Hello and welcome to Lab 4, Circuits and Capacitors. Today we'll be talking about circuits and analyzing what happens. So the purpose of our lab today is to measure the actual values of a conventional current and the potential differences inside of a circuit with capacitors and resistors. We will also be examining the behavior of the resistors and capacitors while in the circuit. To do this, the physics concepts involved are the loop rule, the charge conservation and steady state of a circuit, Ohm's law, and delta V equals Q over C, as well as the fact that the current equals negative dQ over D2. Ohm's law is that V equals I over R, and the loop rule where the delta V of capacitor plus delta V of resistor equals 0. The procedure for our lab in part 1, when we are studying the charge/energy conservation in a series circuit, is to make a circuit with two 1.5 volt batteries and two resistors. Then we will use an ammeter and a voltmeter and record the readings throughout the circuit. We will also be recording the potential difference around the circuit from points A, B, C, D, as in the picture on the right. Then we will be calculating the resistance of each circuit element. In the second part of our lab, we will make a circuit with a 9-volt battery, a 10-ohm bulb, and a 200 microfarad capacitor circuit. We will also do the same thing with a 20-ohm bulb. Then we will charge the capacitor and record the current throughout the circuit. We will also discharge the capacitor as it lights a bulb and record the current. Finally, we will record the voltage versus time as the capacitor discharges and lights the battery. So our observations from the first part is that the current in the first ammeter and the second ammeter is both 0.02 ohms, as well as when we turn it around, it is still 0.02 ohms. The volt of the circuit is 0 volts due to the impact of the resistor when we take out the ammeter and we close the circuit, but the current is still 0.02. The potential difference throughout the entire circuit at the different points that we saw on the previous slide all sum up to 0, and they are as shown in the graph below, where from C to D, the slope is minus 0.09 ohms, and from E to F, its point is 2.014 ohms, due to the way the 47 ohm resistor and the 100 ohm resistor affect the circuit. So, when we attach the voltmeter throughout the different points, we find that the current stays the same. And when connected to the 100 ohm, it's 2.041 volts. However, when we replace this with an ammeter, and we create a circuit with parallel resistors, we find that the current is 0.06 amps, due to dividing the current. The resistance of this is 47 ohms when calculated, and the resistance of 100 ohms is also calculated as 102.05 ohms. The resistance throughout the wire is calculated to be 150 ohms, and the resistance of just the other thing is 0. Of the ammeter, I'm sorry. For part B, our circuit looks as follows, with our charged capacitor, our light bulb, and our ohmmeter and our voltmeter. So our observations throughout this is that with the battery and capacitor, which is connected, there will be no light. But when we take out the battery and we just have the charged capacitor, it lights the battery. So when we calculate we attach an ammeter and see what happens when the capacitor is charging, the current slowly decreases to 0, as well as when it's discharging, it also decreases to 0. So when we see how long it takes with a 10 ohm battery to charge the capacitor and discharge it, it's 9.94 seconds and 11.64 seconds. Then it's 20 seconds and 20.32 seconds, respectively, with the 20 ohm battery. So then when we calculate for the 10 ohm battery 20 seconds of voltage versus time data, with the ln of delta V equals delta V naught versus time plot on the left, we see that the slope is equal to 1 over RC, or 1 divided by 0.02, negative direction. So, what if we were doing this lab in real life and we used an actual ammeter instead of an ideal simulated one? The ideal one would not affect the voltage, but an actual one would, due to resistance within it. So this would make the current lower due to this resistance, and it would have taken longer. The same thing would have happened if we used a real battery instead of an ideal battery. Due to resistance within the real battery, it would take longer to charge the capacitor and wouldn't happen instantly like an ideal battery would. So our lab would not be the same if it was done in real life. To conclude, we are able to analyze the circuit and see how it reacted with resistors and capacitors as well as the steady state law.